Okay, now we're back again after that intro video. I am really happy because it worked. Yay, I just saw it on YouTube. And we are going to be going through 7.1 first, and then I will publish that, and then I will do 7.2 next so that you can get started on your work. So 7.1 gives you a little introduction into rational expressions and radical functions. The first thing you want to understand is what is a square root in the first place. So think about it this way. If you have a square, and that square, pretend that's a square, and that square has an area of 81 inches squared, the concept of the square root is asking you to figure out what side length would cause you to have an area of 81 square inches. And of course the answer is 9, right? So if you have a 9-inch by 9-inch square, then you have a square of 81 square inches. So we write that in a notation that has this symbol right here. This is the principal square root symbol. And we write that the square root of 81 is equal to 9. And the reasoning is that 9 times 9 is equal to 81. Okay? Now that one is called the principal square root, all right? So this is the principal square root. The principal square root is also called the positive square root. Because the output is positive, right? Now, if you want to look at the other square root, the negative square root, the negative square root is the one with the negative on the outside. So what this is saying is that, yes, it's true that 9 times 9 is equal to 81, but there's also this other number out there, negative 9. And negative 9 times negative 9 is also equal to 81. But this one is not principal, because when you're dealing with squares in real life, the side length of a square is of course going to be positive. So the default is that the square root is going to be a positive output. It's only a negative output if you have a negative sign in the front of it, okay? So if there's a negative sign, then it's going to be negative. And that's pretty easy stuff, but we also want to consider what happens if you put the negative inside, okay? So let's compare that to the square root of negative 81. This is asking you to find a number that when you multiply it by itself is going to give you an answer of negative 81. And that's impossible, right? Because a positive times a positive is a positive, and a negative times a negative is a positive. So if you multiply any number by itself, you will always get a positive output. So this does not exist. Does not exist. This is not a real number, okay? That's another way of saying it. Not a real number. You may have already learned about imaginary numbers in another class, and so this actually can be simplified using imaginary numbers, but we're not covering imaginary numbers. We're not focusing on that. That's something you will cover in college algebra. So for the sake of this class, when you come across the square root of a negative number, you can say it does not exist. You can say not a real number. What you do not want to say is no solution. Why? This is an expression. It is not an equation. Because it is an expression, the question is whether or not it can be simplified, not whether it can be solved. Only equations are solved. Expressions are simplified, right? Okay, so now we're going to get into a little bit more complicated information. We want to talk about next are radical functions. Radical functions are simply functions that involve radicals or square roots or cube roots, right? So when you see the word radical or you hear the word radical in math, what that does not mean is some guy with spiky hair, right? In this case, in math, it means that you have the square root or cube root or fourth root. Of course, nowadays having spiky hair, and actually when I was growing up, spiky hair was not necessarily radical. I don't know why it came to mind for what is radical. Okay, anyway, that's beside the point. Let's look at a radical function. So in your textbook, there are several examples given. I will come up with one here pretty simply. Okay, so I'm going to use this one. It doesn't have to be any particular example, and you don't need to necessarily replicate this concept, but number 123 on page 593 is about embroidery. I don't care if you become an expert in embroidery. What we care about here is whether or not you understand how to use a rational function. And so the idea is that if you have a circle, the radius of the circle, which is defined as r, the radius of a circle is a function of the area of the circle, in the same way that the area is a function of the radius. It can go back and forth. So the radius of the circle is, if you take the area and you divide it by pi, and then take the square root of all of that, you end up with the radius of the circle. So let's say in this example, they said that we have a circle with an area of 38.5 inches squared. 38.5 inches squared. This is the area. Now, area in this problem is represented by A. So the natural question that is going to follow is, what is the radius of the circle that has an area of 38.5 inches? So we simply replace A with 38.5, divide by pi, and then take the square root. Now notice something about my notation. It's not ambiguous, and that's something that some of you really need to focus on. Writing your notation in a way that it is very clear what you are communicating. And here I have a fraction, and that fraction is inside the square root. And I made my square root symbol nice and big, right? So it covers the entirety of the fraction this way, and it also drops down the entire length this way, and that way it's really clear that the entire fraction is inside the square root. Don't make the square root a little stumpy and short right here if you have a fraction, because then it can become unclear. It could be unclear as to whether or not the square root applies only to the numerator or to both the numerator and the denominator. And in this case, it applies to both the numerator and the denominator. Okay, so what then you need to do is you type this in the calculator. And I did not bring my calculator with me today. However, I do have my calculator app, which was coming up on my computer before, but now that I'm using this second application, it is not doing. Well, that's exciting. Well, as it turns out, I have the answer. So if you were to type this in the calculator, and you were to round to the nearest tenth, it's going to be 7.0 inches, and so you can determine it that way. But note to self, next time when I'm lecturing, I need to bring my calculator with me. And the calculator on my computer is not adequate right now because this application that I'm using to record has taken over my screen and will not allow me to multitask with other applications. Alrighty. So now the question is, what does the square root function look like when it's graphed? This is one version of the square root function. This is not the parent function. This one is actually manipulated because you have the variable, it's divided by pi before you take the square root. Okay, so that would be a shrunken version of the parent function. So what I want to do is teach you the graph of the parent function, the very basic square root function, and then we'll just look at how to shift it left and right and up and down. It's not a graph that you need to master for this course. The two graphs you need to master are the graphs of lines and the graphs of parabolas. So in this course, you will be introduced to other graphs, such as the absolute value graph, or the square root graph, the exponential graph. Those other graphs are necessary for you to be introduced to at a lower level like this. But those will be explored higher up. At this level, what you really need to master is how to graph a line well and how to graph a parabola well. And we'll study the parabolas again later. So that's a future chapter, is when we get back to parabolas. But right now, we're just going to look briefly at how to graph the square root. Okay, so this is what the square root function is. F of x equal to the square root of x. So if you're going to graph a function, it's best just to start with an xy chart. And you need to pick values of x that are actually in the domain. We've had one domain violation issue so far in this course, and that is we do not divide by a negative number. No, we do not divide by 0. I'm sorry, I started thinking about this one. We do not divide by 0, right? So when we looked at rational functions, the big thing that we had to watch out for is do not have 0 in the denominator. Well, here, with square roots, you can take the square root of 0. The square root of 0 is 0, because 0 times 0 is equal to 0. But you cannot take the square root of a negative number without going into imaginary numbers, and we are not using imaginary numbers. We're using real numbers. So what I want to do is pick values here that are going to be non-negative. And the other thing is, since I'm graphing this by hand, it's a whole lot more convenient if I pick numbers that are perfect squares, because then I can graph using integers. Whole numbers, actually. Okay, so I'm going to use 0, that's a perfect square. 1, that's a perfect square. 4 and 9, that's good enough. So the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. And now I have a table that's going to give me my graph. These are all non-negative, which means that I am going to be entirely in the first quadrant. So here's 3, here's 3, 6, and 9. So my graph starts at 0, 0. Then it goes to 1, 1. Then it goes to 4, 2. So this point right here is 4, 2. And then it goes to 9, 3. Right. So that's the graph. It's that simple. Now the graph does not continue down. There should be no arrow going this way. It starts here at the origin and then it goes to the right. So the domain is going from 0 to infinity. The range is also going from 0 to infinity. The other thing you want to notice is that this graph is half of a parabola on its side. So you can imagine an entire parabola right here. This is half of the parabola. So it should look like half of a parabola tipped over on its side. That's what it looks like. Now you can shift this graph left or right, up and down, in the same way that we shifted graphs before. So let me just move over here now. Okay, try not to be too crooked here. All right, over here I want to look at what would happen if I were to take the graph and transform it. Okay, well, I should call this G instead of F. This will be a different function. So if I were to take x, let's see, minus 2, minus 1. Okay, so I actually have two transformations here. I have a right to left shift, and I have an up and down shift. Look at my notation. The square root stops here, okay? So where the square root stops, whatever is underneath the square root, think of it like a shelter, like a roof. Whatever is underneath that square root is inside the square root, and this -1 is outside the square root. It's like an afterthought, okay? So this is inside the function, and this is outside the function. What that means is that this is a horizontal shift and this is a vertical shift. And if you remember when we looked at horizontal and vertical shifts earlier in the course, horizontal shifts were counterintuitive. So whereas this says -2 and you might think, -2, move left 2, it's actually going to move right 2. And then this one is going to move down 1 because vertical shifts are actually intuitive. So if it says -1, it actually does mean go down 1. So what I'm going to do is I'm going to take the graph over there, and it's like a click and drag. I'm going to move it right 2, down 1. So each one of those points is simply going to go right 2, down 1. So where does 0, 0 go? 0, 0 moves to the right 2 and down 1. And that puts you at 2, -1. 1, 1, if it goes right 2, down 1, ends up at 3, 0. And then 4, 2, if you go right 2, down 1, that ends up at 6, 1. So here's 6, 1. And then the last one, 9, 3, right 2 takes 9 to 11. Down 1 takes 3 down to 2, so that's at 11, 2. 7, 8, 9, 10, 11, 2. All right, so here's 11, 2. So here's the graph. The graph starts, in a sense, mid-air right here. It's still the same shape. It's that parabola that is on its side, half of the parabola only, the upper half of it. But that shape from here to here, all it did was shift right 2, down 1. So if you want to look at this in a little greater depth, I would highly recommend you open your textbook. Look at example 3. Look at example 4. Example 3 goes over the parent function. So the parent function was this one right here. That one is in example 3 on page 584. On page 585, you see all the transformations. Okay, so I did that a little out of order because I did the graph before evaluating the function, and the graph was objective 3, and the function evaluating was objective 4, but that's okay. We're good. All right, now we're moving on to the higher roots, cube roots, fourth roots, fifth roots, nth roots. So the geometric understanding of the cube root would be that the cube root is if you have a volume of a cube, like the volume of your cube would be 8, for instance, what side length would produce a volume of 8? And the side length of a cube would be 2, right? 2 times 2 times 2 for a cube is going to give you a volume of 8. That's the concept of a cube root. So the square root is what I call an even root because the little number on the inside of the cleft is an implied 2. Okay, let me show you what I mean. When you draw the square root symbol, you produce this little cleft right here, okay? And into this cleft goes a number. Now, if there is no number, the assumed number, the implied number, is a 2. That's the square root. You do not need to write the 2, okay? It's not usually written, but it's like an invisible 2 there, okay? Now, if you put a cube, or 3 in here, that becomes a cube root. And if you put a 4 in there, it becomes a fourth root. And you can get all the way to what's called the nth root, which is just pick your number and put it there. But the third root, the fifth root, seventh root, these odd numbers, third root, fifth root, seventh root, these are the odd roots. They're not taking a root of an odd number. The number up here itself is odd. Okay, and what's special about the odd roots is that you can have the odd root of a negative number, right? So you can have the cube root of -8 because -2 times negative 2 times negative 2 is negative 8. You can't have a negative number inside of an even root. So the fifth root of negative 32 is negative 2, because negative 2 times negative 2 times negative 2 times negative 2 times negative 2, that was negative 2 5 times, is negative 32. So you can have odd roots of negative numbers, and it's not a problem. You may have noticed from the syllabus when I gave you the recommended reading that I skipped example 2. So why did I skip example 2? Example 2 is a more technical case where the variable inside the radical could equal a negative number, all right? And we're not going to study that particular case because it involves you having to use an absolute value symbol when you simplify, and that's just, we don't need to go there. So to make things a lot easier, we're going to have this disclaimer, and the disclaimer is that we are going to assume all variables are non-negative numbers. So if the variables are non-negative numbers, then we do not have to use the absolute value symbol when we simplify, okay? So if you're going to simplify the square root of 36x to the 6th power, the square root of 36 is 6. What about the square root of x to the 6th power? X to the 3rd times x to the 3rd is equal to x to the 6th. Remember that. So because x to the 3rd times x to the 3rd is equal to x to the 6th, what that means is that the square root of x to the 6th is equal to x to the 3rd, right? So when I'm simplifying this, the square root of x to the 6th is going to be x to the 3rd. So this simplifies to this. And we do not need to use any absolute value symbols when we simplify this, because I'm going to use this nice disclaimer. So for this whole course, we're going to assume that all the variables inside the square roots and the fourth roots and all that, actually all the roots, we're going to assume that the variables are non-negative numbers, because it will make our lives less complicated. It will be easier. And you may be not having this disclaimer in college algebra, but for the sake of intermediate algebra, this is totally fine. Okay, so what we're going to do is we are going to now look at how to simplify a cube root in a similar manner. Okay, so let's say you end up with the cube root of negative 8, a to the 9th, b to the 15th. Okay, so the cube root of negative 8 is negative 2. We talked about that earlier. Negative 2 times negative 2 times negative 2 is negative 8. But what about these? Well, here's the trick. You take this number here, 9, and you divide it by this number, 3, and you end up with 3. And what that does is it tells you that if you have a cubed times a cubed times a cubed, it will equal a to the 9th. And similarly, you can take 15 and divide it by 3, and you get 5. And that tells you that b to the 5th times b to the 5th times b to the 5th is b to the 15th. Now, if that sounds a little complicated to you, a little stressful, this is a little story analogy that Dr. Rachel Graham told me at one of our cram jams, and she said it this way. So let's say you're at a carnival, and in order to get on the ride, it costs you 3 tickets. Okay? Now A, we'll call him Adam. Adam has 9 tickets. How many times can Adam go on the ride? He can go on the ride 3 times, right? Because each of those 9 tickets have to be bundled into groups of 3. And then each of those bundles of 3 allows him to go on the ride once. Okay? So you have a cubed. Now this is Bob. And Bob has 15 tickets. So since 15 divided by 3 is 5, that means that Bob gets to go on this ride 5 times. Ta-da! And that's how you can simplify that pretty easily. It will get harder to simplify these, but in 7.1 it's a pretty straightforward process. So you can look at how to simplify a variety of different examples. If you flip through the examples in your book, I urge you to stay in your textbook. It is a really important skill to learn how to use your textbooks and to use them well. Even if you go beyond math classes into the real world, there are books, manuals, references, procedures. There's a lot of jobs that have a lot of manuals and procedures and reference books, and to be able to go through that information and process it for yourself and not have somebody else spoon feed you, that's a really important skill. It's like going out and getting your own food, foraging for your own information. Okay, we are not graphing the cube root function, so you can skip that as you're looking through everything. And for nth roots, that last objective, starting on 589, what that is just covering are the higher roots other than cube roots, so the fourth roots, the fifth roots, etc. So you can look through those. I'll give you one example here. So let's say you want to have the fourth root of 16c to the 24th. Okay, so the fourth root of 16 is 2, because 2 times 2 times 2 times 2, multiplied 4 times, right, is going to be 16. And then how do we do this? This 24 gets divided by 4, right? This ride costs 4 tickets. And Charlie has 24 tickets. 24 divided by 4 is 6. So C to the 6, like that. And so that's pretty straightforward right there. And that's most of what you need to know. When I'm looking at 7.1 here in the study set, you'll be looking at number 63, how to evaluate the function. You're going to use the same procedure as we did before. Make sure you show your evaluation step, the step where you actually substitute the values in. I'll give you an example. I will do number 66 for you real quick. Okay. So we're looking at number 66 from the book here. S of A is equal to, this is negative cube root. Notice the negative is on the outside. 32A. And we are supposed to evaluate in part A, S of negative 2, and in part B, S of 2. So part A is to find S of negative 2, and in part B, S of 2. So this is how the work is shown. You take this same function, you replace A with negative 2 here. Notice the square root continues, it covers everything. So imagine rain falling. These do not need to get wet. Okay? And then here we have negative cube root of 32 times 2. So this ends up being the cube root of a negative 64. And the cube root of negative 64 is negative 4. So the negative 4 has this negative now out in front of it, and you can get 4. You may be wondering what of all that you need to show. Okay, so you need to show this part, and then you need to get to your answer. These other parts right here are optional intermediate work. Definitely show the substitution, and then show this answer. And then over here we have cube root of 64. Cube root of 64 is 4. There's still that negative out in front though. And again, you only need to show, you can show this part, and then you can show this part. So there will be some evaluating problems. And then also you have 67, which you get to evaluate using a calculator. So for that, again, you're just going to show that first line. The first line is where you actually plug in the values, And then after that, you use the calculator. So it's better to not use the calculator on these problems because the directions say do not use a calculator. Of course, that's something that you would have to do on your own. If it says do not use a calculator, what it's trying to do is it's trying to teach you a skill that is going to be used later. And so it's worthwhile to follow the directions. If the directions say do not use a calculator, then you should not use a calculator. If the directions say use a calculator, then you should use a calculator. Just follow the directions. Okay, so there will also be little videos, of course, on My Open Math. They can walk you through individual problems in greater detail, but I hope that this gave you at least the grounds you need to get through 7.1. And I will do another lecture next for 7.2, and I will get that posted as soon as I can. All right, I will see you soon.